Hello, this is the Tutoring Club's video on limits and continuity. Just to give you an overview on what I'm going to do, I'm going to go through every single objective for the power focus area and then go through the diagnostic, so hopefully you can gain enough of an understanding to pass the content assessment. So, the first objective that we're going to go through is estimating limits from graphs. So, the first thing we want to do is we're going to talk about limit notation. So basically, when you look at a limit, it's always going to look like this, right? It's going to have the lim, which means limit, of course, and then it's going to have the x to a, where x is just going to be whatever your independent variable is on whatever graph you're using. Generally, it's just going to be x, and that's what I'm going to use throughout this presentation, just for the sake of simplicity. A is whatever point on the graph that you're going to be approaching. For example, if you're trying to find the limit at the point 5, right, it's going to be the limit as x approaches 5. F of x, this is just your function, right? Pretty obvious. And then C is the answer to the problem. It is what the limit is when it has been evaluated. So there are multiple ways to take limits. For example, there are two-sided limits, which pretty much just means it's a point where the graph is continuous, which is something that we're going to go over in a moment. So, assuming the graph is continuous here, we can see that the limit, you can see that, right, both sides of the graph go into that one point. So if we took the limit as this function approached negative 0.7, right, so we'd write it as the lim x approaches 0.7, right, of, we'll just call this function f of x, is equal to this right here, right, negative 4.508. So pretty much all you have to do for two-sided limits like this is you just plug in x into the equation, whatever x is approaching, and generally that's going to be your limit. Note that there are a few exceptions here. For example, you might have something like a hole in your equation. A hole is pretty much just when a function is undefined at a specific point. If a hole is there, then if you were to plug x into the equation, it would come out as undefined, but that does not mean your limit is undefined. What you would have to do in that scenario is pretty much you're taking the values of points extremely close to this. For example, as I let's just assume that instead of actually evaluating to negative 4.508, the function at negative 0.7 was a hole. Rather than just plugging negative 0.7 into the equation, what you would do is you would plug numbers that increasingly approach 0.7, which is where the as x approaches comes from in the limit thing. So you would plug in, for example, negative 0.69, negative 0.699, and then so on, right? And then you would also plug in numbers increasingly getting close to it in another way. For example, from the opposite direction, I mean, which would be 0.71, 0.701, and then so on. Now, finding two-sided limits is the more simple of the two ways to find limits. There's another type of limit that you have to try to find called one-sided limits. One-sided limits you're going to see exclusively in piecewise functions, because one-sided limits only come about when there is a jump in the function. So pretty much what you can do is you can find a limit from approaching from one side and a limit approaching from the other side. So right here, uh, so what you would do in this case, in this scenario, is because how most piecewise functions work is that only one of the points where the function ends off actually has the point. What you're going to do is you're going to use the method that is from two-sided limits where there's a hole, and you'll see that basically you can do it just from one side and make that estimation from there. So for example, if we wanted to find the limit as from this function, we would write it like this. The limit of as x approaches 3, and since it's coming from this side, it's coming from the lower side, you would write this right here, which pretty much means it's coming from the left, it's coming from the lower, closer to the negative side, of f of x is equal to whatever. In this case, it would be 1.1, since in Desmos, I configured it so that I could just show the limit on the point. Similarly, you would do, and pretty much how you would find that, similarly to two-sided limits, is you would just continuously get closer to 3, right? 2.9, 2.99, and so on. Now, you would do and it would be pretty similar if you're trying to find a limit from the opposite direction. So, you'd write it like this. The limit as x approaches 3 from the right, because this is the right, more positive of the two, of f of x, right? And pretty much you would use the same method here, right? It equals, in this case, 0. Pretty much you would just do the same thing, right? 3.1, 3.01, and so on. Moving on to our second objective, determining if graphs are continuous. So there are 3 main conditions for continuity. One is that the value f of x must exist at that point. That is, there cannot be a hole there, right? So you plug in like f of 5, for example. F of 5 would have to output a number. It has to exist. The limit of f of x also must exist at that point, meaning you write the limit, right, as x approaches 5, right, of f of x would have to equal some number a, right? And at that point, the limit of f of x and f of x itself must be equal to each other, because for example, let's just say we have like a basic parabola here, and there's a hole there, and there's the actual value of x is right here, just due to some special reason. You can see that it fulfills the first 2 conditions, and but it doesn't fulfill the third condition, meaning that this wouldn't be continuous. And for those wondering, continuity just means it's a straight line. There's no gaps, right? No gaps, no holes, whatever. So those are the 3 conditions for continuity, right? That limit of x, the limit as x approaches, let's just say 5, and f of x, right, are equal to one another, right? The third objective is using the intermediate value theorem and the mean value theorem to evaluate statements. So the intermediate value theorem is basically, all right, you have a line, you have a point between these 2 lines. If you draw a line, assuming that the line is continuous, it will pass through this line at one point. That is all the intermediate value theorem is. You have a point above a point and a point below a point. You assuming you connect between those 2 points, it is continuous. It has to pass through that third point. Mathematically, that would look like you have a function f of 1, right, is equal to, let's just say, I don't know, 5, and f of 3, or f of 2, is equal to 6, assuming that f of x is continuous. Note that it is only when f of x is continuous. This does not apply when it's not continuous. Then at some point, at some value between 1 and 2, f of x has to equal 5.5, right? That's pretty much all the intermediate value theorem is. The mean value theorem is a bit more complicated. Pretty much what it's saying is, assuming, let's just say, again, function f of x, assuming function of f of x is both continuous and differentiable, both continuous and differentiable, you can take any function, assuming f of x is both continuous and differentiable, right? Let's just say it's a function that looks like, I don't know, this, right? You can take point A, let's just say point A, and then point B, right? And then let's just really quickly, f of A, f of B, and basically you can take the average rate of change, which is just the rise over the run, right? The difference in A, right, which is just it's just the difference in y over the difference in x, which is f of b minus f of a over b minus a, right? Average rate of change, rise over run, right? You can take this value and basically at least one point, the slope, the average slope, the value of this is going to be equal to the instantaneous rate of change, which is the, which would be the slope at any specific given point, right? You can even see kind of like right here, right? It's sort of very similar to that. That's all the mean value theorem means, is that at one point, the average rate of change is going to be equal to the instantaneous rate of change. And if you don't know what differentiable means, you don't have to worry about it. That's not something you're going to have to be thinking about, at least for this content. Now, let's move on to the diagnostic. We're just going to go through all 10 questions, and we'll see. So this first question. Consider the function in the graph to the right. What is the limit as x approaches 0? So, as we covered earlier, we're looking at here. And just from the graph, you can see that there's no holes there, there's no jumps, there's not even an asymptote. So we can just plug in x, or see what x is at 0, and it appears to be 2, which would be our answer here. Selected values of the function f are given on the table to the right. For which of the following values of k must f of x equal 1/2 at least twice on the interval 0, 2? So, pretty much this is another intermediate value question theorem. intermediate value theorem question. Pretty much all we're answering here is that, okay, what point do we need to make, right? So, like, we're looking at 3 points, right? 1 and 2, right? So this is 2, this is 1. All we have to do is, let's just make this imaginary line equal to 1/2. All we have to do is find a value that goes below this line and then goes below this line. Here, we can see that while 1/2 does make it touch the line, it does not make it go through the line. And all values of 2, 3, and 1 also would just, right, it would be like that, and then that, right, for 2, 3, and 1, pretty much. With the value of 0, it would have to go below the line, meaning that 0 is the correct answer here. Consider the function in the graph to the right. What is the limit as x approaches -1? So this is something that I didn't cover in the initial finding two-sided limits, but asymptotes, the limit as an asymptote doesn't exist. So we can see right there at -1, there's a vertical asymptote, meaning it doesn't exist. Also, excuse what I said earlier, I mean at vertical asymptotes. Limits at horizontal asymptotes do exist. So the limit does not exist. This one's pretty simple. The limit as x approaches 2 is equal to what? So here we can see that there's a jump at the specific point. We're not looking for the value of the black dot here. That would be the value of f of x on this graph. X approaches 2 would still be the estimation here. So that would be 0 because, as you can see, the whole would be on 0. The function f is shown in this graph below. On which of the following intervals is f continuous? So we have a bunch of answers here. We'll just run through them all. Obviously, we'll run through none last. So x is greater than or equal to 1, and x is greater than or equal to 2. So we already know that when x equals 1 and x equals 1 here and x equals 2 here, we can see that there's a jump at x equals 1 and a jump at x equals 2. Therefore, it is not continuous. So this is not the right answer. Next, for the interval negative x, -1 is greater than or less than or equal to x, and 0 is greater than or equal to x. We can see, again, there is a jump at 0. Therefore, x is not continuous at 0, right? And also note that the limit doesn't, the limit from both sides of f of x also doesn't exist at -1, though it does exist if you're going from the right. So here's the third one. 2 is less than or equal to x, and 3 is greater than or equal to x. We, again, saw earlier that there is a discontinuity at number 2, meaning we can immediately cross this off the board, and the same thing as I pointed out with -1. The actual limit doesn't exist. It would be the limit coming from the negative side, or coming from the right. Now we have the last one. 0 is less than x is greater than, and 1 is greater than x. So while there is a discontinuity at number 1, since it's only less than 1, we're not including the number 1 here, meaning the discontinuity is not included in this interval. And it's the same thing with 0, because it's not greater than or equal to 0. It is not included. So discluding both of those points, the function is in fact continuous on this interval, meaning that this is the answer. All right, this one has multiple answers. Consider the graph of the function to the right. At which values of x does the limit exist, but the function is not continuous? So let's go through each one individually. X equals 3. So there's a hole here, meaning the function is not continuous. However, there's no jump, meaning there's no jump or asymptote, meaning the limit does in fact exist here. So x equals 3 is correct. X equals 1. While there is a jump here, it is not a jump with a line. And again, there's a hole there, meaning it is not continuous. However, there's no asymptote or jump like this one, meaning yes, this is correct. X equals 2. There is a jump here. The limit does not exist, and it is also not continuous. This is not correct. X equals 4. The function is technically continuous at this point. However, the limit does not technically exist from both sides. So this is not correct, and it is the same case with 0, where the function is technically continuous at this point. However, the limit does not exist. Limit from both sides does not exist, which does technically actually mean it's not continuous. But, you know, for the sake of whatever we're talking about, I'll just say that it is technically continuous at that point. The graph of the function g of x is shown below. At what values of x is the function g of x not continuous? Pretty much here, there's no holes, whatever. We're just looking for vertical asymptotes, because horizontal asymptotes do have limits, and they are continuous. So we're just looking for the vertical asymptotes, meaning a and b are the only vertical asymptotes, meaning the correct answer is a and b only. For h of x graph to the right, evaluate the limit of the limit as x approaches negative 4x from the right, or from the left, I believe. So pretty much we're just, I mean, it doesn't matter because the limit, what direction is doesn't matter technically, because the limit as it approaches from the right or from the left, they're both the same. It's not negative 5, it's just 5. It's a vertical asymptote. It's going to forever approach that value of 5. For h of x, graph to the right, evaluate the limit as x approaches infinity for h of x. So there's a vertical asymptote here, meaning as the limit approaches infinity. Sorry, I misread this in the last question. So actually, this is not correct. It's actually the limit does not exist. Sorry, I read that as x approaches infinity. This, again, it's an asymptote there, and it is never going to touch that value. Therefore, the limit does not actually exist there. This is the question talking about as x approaches infinity. It's going that way. The limit is 5. And our final question. This is the last slide of the slideshow. So after this, I'll be signing off. Consider the function f of x graph to the right. At which values of f of x is f of x not continuous? Select all that apply. Pretty much, we're just looking at the 3 discontinuities here and just what values they're at. So this first discontinuity, it's at -3. The second discontinuity is at -1. And this final discontinuity is at 3. And just to be sure, we'll check 2. That is continuous. We'll check 0. Again, continuous. And those are the right answers. All right. Thank you for watching. That is the whole video. And yeah, that's limits and continuity.